Hello everyone and welcome to this video covering Newton's method. Newton's method is a process that involves just numerous iterations through the use of a particular formula, particular rule, to approximate the zero of a function. And that's really what we're going to be focused on with this video. Now, the main thing you have to remember that the goal of Newton's method is to approximate c, which is the x-intercept of our function. So we're going to try to approximate that particular value. And the way we do that is we go through and we will make our initial guess. We will pick a number that is, for lack of a better term, close. And that's a very nebulous term mathematically. But we pick a value that is close to c. And in this case, I happen to pick this value x1. And what happens is we're going to approximate this x-intercept, because remember, the tangent line at a particular point is a decent approximation of a function. So we go through at x1, we calculate its tangent line. And from there, we go through and we find the x-intercept of the tangent line here, and that becomes our second guess for our value of c. And then we repeat the process over again. So at x2, we go through, hit the curve, calculate its tangent line, and then this point right there, the x-intercept becomes x3, and we just continue this process back and forth until we get to a desired accuracy that is often going to be expressed in the problem. Okay. Now, the thing to remember about Newton's method, your calculator, this is something that your calculator uses to go through. It obviously can do it very, very fast when you find the zero or root feature, because one of the things they ask you to do is they ask you for a guess, and that is the x1. But the other thing you have to remember is Newton's method is very fast. It will zoom in on a zero rather quickly. There are instances where it can fail to find the zero. One of those happens to be if you just happen to be situated where you identify you pick a point and the tangent line at that point intercepts your second guess, but when you do your second guess, when you use your second guess, it goes back to the first guess. So you have that situation. The other thing is given situations, sometimes if you are not close enough to a particular zero, the zero you want to locate, you could end up zooming into one that is that's not, you'll find a zero, but it won't be necessarily the one you want to find. But this is the process. What we just looked at here does illustrate that process of Newton's method in terms of how it goes forward. So on the last slide, we talked about the whole process that you go through for Newton's method. In this case, let's take a look at the actual calculations that are going to take place. So I have the equation y equals f of x. And I'm going to go through and find the tangent line to that curve at a point where x equals x1. And so when I plug that into y equals f of x, I get the point x1, f of x1. And my slope is going to be f prime of x1. Now, you may remember the point-slope form of a line where x1 and y1 happen to be the coordinates of a point. So if I plug that directly into my equation, what I have is that I'll end up with y minus f of x1, that's my y coordinate, equals f prime of x1 times x minus x1. And now what I'm going to do is I want to identify the x-intercept of this tangent line. So really what that means, what's happening there, remember the x-intercept is going to happen when y equals 0. So what I'm looking at now is the opposite of f of x1 equals f prime of x1 times x minus x1. And I'm going to solve that for x. That's what I want to solve it for. So to do that, I'm going to go through. I will divide by f prime of x1. And when I do that, I'll have negative, the opposite of f of x1 over f prime of x1 equals x minus x1. And then I add, and then when I go through and add x1 to both sides, I end up with x equals x1 minus f of x1 over f prime of x1. And that right there, this, when you take this and you find the equation of this tangent line here, when you find this x-intercept, that value is going to be our next guess. So let's take a look at the process of Newton's method. When doing Newton's method, we're going to first make an initial estimate, and f, which is going to be x sub I, as to that is close to c. That's, again, define the definition of close can be somewhat nebulous, but we want it to be relatively close. Okay. Determine a new approximation by using this recursive rule that the x sub n plus 1 is equal to x sub n minus f of x sub n over f prime of x sub n. And when this absolute value between two consecutive guesses is within the desired accuracy, then the last guess is going to be our final approximation for our zero that we have for this particular function. The key to doing Newton's method, though, is to getting the iteration formulas that you need to work with in the problem. And so remember on this one, you've got to recall that all of them are in the form x sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. And so whenever we're finding the iteration formula, we need to know what the derivative is. So if this first problem, f of x is x squared minus 2, and therefore f prime of x is equal to 2x. So our iteration formula in this case is going to be x sub n plus 1 equals x sub n minus x squared minus 2 over 2x. What I'd like you to do right now is pause the video, and I'd like you to go and find the iteration formulas for number 2 and 3. And once you have those, come back, we'll take a look at what you came up with. Okay, welcome back. In this case, the first one that I asked you, the first thing I want you to recognize on this one is that I did forget the ends on those, so those should be on there too. If you had questions about that, I hope that you recognize that. Anyway, number 2, what you have to do on that one, remember you're taking the derivative of cosine of x. Derivative of cosine is negative sine of x. So x sub n plus 1 is going to be x sub n minus cosine of x sub n minus sine over negative sine of x sub n. And when you simplify it, you get this. And if you wanted to, you could say that's going to be x sub n plus the cotangent of x sub n. That would be fine too. Working with this second one, forgot my parenthesis there, the derivative of f comes out to be 1/2 x to the negative 1/2, because that's x to the 1/2 power, which is the same as 1 over 2 square roots of x, where the 2 square roots of x is in the denominator. So setting up my iteration rule, x sub n plus 1 equals x sub n minus the square root of x sub n minus 3 over 1 over 2 x times the square root of x sub n, which when you simplify it, you go through dividing by this fraction is the same as multiplying the numerator by 2 times the square root of x sub n. And so I will end up with this, and that will simplify to be that. Okay. Hopefully you came up with that. If those answers don't match yours, double check, take a look at the calculations, see if you can identify what mistakes happened. Now let's go through this process of Newton's method to approximate a zero, and we want to go through until we have an accuracy of where the difference is less than 0.01. So we're within 1/100th of the actual zero of this function, which we could go through and do on our own. This would not be a hard one to do. Anyway, so one of the things we have to do, they're telling us we're going to let x1 equal 1. And the other thing I want to do is I want to go through and set up my iteration rule. So in this case, f of x is x squared minus 2, so f prime of x is 2x. And so again, as we saw before, in this case, we're going to use that x sub n plus 1 is equal to x sub n minus x sub n squared minus 2 over 2 times x sub n. So there's our iteration rule. Now on this particular problem, they did tell us that our first guess, so when n is 1, x1 is 1. Now if I plug 1 into my function, 1 squared minus 2 is going to be negative 1. And if I plug it into the derivative, I am going to get 2. And so therefore, this particular problem here, the f of xn over f prime of x sub n, is going to come out to be negative 1/2. And so what I have here, my next guess is going to be 1 minus a negative 1/2, which comes out to be 3 over 2. So in this case, our second guess, when n is 2, I'm going to use 3 over 2. Well, those clearly are different by more than 0.01. Okay, so now I plug 3 over 2 in for x. And when I plug 3/2 in for x, f of 3/2 is going to be 9/4 minus 2, which is going to end up being 1/4. And when I plug 3/2 into f prime, I get 3. And so this time, our problem here, f of x, the fraction that we get, f of x sub n, we're going to get 1/4 divided by 3, which is 1/12. And so what I'm going to have is 3 over 2 minus a 1/12, which will be equal to 17 over 12, or about 1.416667. So this was when n was equal to 2. So now we're going to look at what happens with n equals 3, because that's now we now have our third guess. So when n is 3, I'm going to put in the 1.4166, it comes at 67. Okay, I'm going to plug that into the function, and when I do that, I will get 0.006945. When I plug this, the 1.416667 into the slope, I will get 2.83334. And then when I calculate the ratio between the f of x sub n and f prime of x sub n, I will get 0.002451. And therefore, when I make my take my difference, the 1.416667 minus 0.002451, calculation-wise, I will get 1.414216. And so what would be our fourth guess on this one, when n was 4, would be 1.41 4216, which is definitely within our range. So our 0, in this case, the square root of 2, is approximately equal to 1.414216 by using Newton's method. Now, pause the video, make sure you're comfortable with the calculations as we went through there. And once you do, we'll move on to the last one, which talks about the different ways that we can apply Newton's method to find other features. Now, other applications that we can use Newton's method on. Number one, we can use Newton's method to find the intersection point between two functions. And the way that works is really we define our, remember the Newton's method will find the x-intercept of a function. So if I want to find the intersection point between two functions, f and g, then I'm going to define a new function, h of x, which is f of x minus g of x. This h of x will be 0 when f of x and g of x are equal to each other. And so therefore that would be at 0. And so our iteration rule in this would come out to be that x sub n plus 1 equals x sub n minus h of x sub n over h prime of x sub n. Another one thing that we can do with the Newton's method, it's another process we have, is it can find a relative max or min of a function. Okay, given that the function, again, the function has to be differentiable. If the function's not differentiable at that, remember when we talked about, when you look at these things, when we have these curves where we can have a high point or low point, we could have a place where it has a cusp. But if we don't have a cusp, then we can use Newton's method because it's differentiable and so the derivative is defined. And we can go through. Now, the high point and low point are going to be when that derivative is equal to 0. So if I want to find a relative max or min, what I can do is of a particular function f of x, that the difference is going to be that now I'm trying to approximate the 0 of the derivative. I want to find that 0. I want to find where f prime of x equals 0. And so my iteration rule in that case is going to be x sub n plus 1 equals x sub n minus f prime of x sub n over f double prime of x sub n. And that's how we can go through, and that's what actually your calculator uses to identify the intersection and the relative max or mins of a particular function. Okay. So with this does conclude the video covering Newton's method. Again, if you have questions, make sure you write those down. And if as long as we're okay, if you want to review this, go ahead. Otherwise, we will see you in our next class.